Hello viewers, welcome. Let's continue the tutorial we are having on permutation and combination. This is episode number 9 of the series we are having. And in this series, we want to have introductions into the various types of what? Permutation. For the first type, it has been what we have been dealing with in this previous episode. So the permutation can be classified in three categories. So the first category is permutation of n different objects where repetition is not allowed. If you follow the tutorial from the beginning, you can see there are ways by which we can have selection from n different objects, whereby we are going to pick either all the n at a time or r of them at a time. That was what we have as the first instances following the fundamental principles of counting. Then number 2, permutation where repetition is allowed. So far, we have not dealt with any question that have repetition being allowed, apart from the sense where we have it under fundamental principle of counting with no formula pattern being developed. Then number 3, permutation when the objects are not distinct. Remember, the beginning definition was permutation is just the arrangement of n distinct numbers or objects. It means all the objects we are going to be arranging are all different. There is no one having itself being repeated. But in the case of this, there should be or there will be some instances whereby some of the objects to be selected from are going to have repetition, or they are, yes, let's put that way, repetition, as in the case of ball, ball. You can see if you are asked to arrange this four-letter word, picking 2 or 3 at a time, we can see we cannot distinguish between the first L and the second L. So that is not distinct, meaning the L's are of different nature. Now, in the first instance, this will just be like a recall of what we have done previously. If I have n different objects whereby I am going to be selecting r of them, there are n different objects to be selected. All right, so from recall from the previous episode, here we can say that the representation of n different objects being available with selection or the arrangement of 3 at a time, of r of them at a time, is represented by n permutation r. We represent n object to be selected from, that is the let's say the mother set as a universal set, right? With r objects selected at a time without repetition. There is no repetition. Now we mentioned the word selected. So there is a condition here in which order matters. The order matters simply means that you are referring to only permutation. Selection is done with combination. But if we say selection, then we are going to consider where the order of arrangement matters. So A, B is not the same as BA. But when it comes to combination, AB is the same as BA. So order in this case is different. Now, this will be represented by n combination r equals to n factorial n minus r all factorial. Remember how this formula all came about is in the first episode, how we derived it. So this is what we are going to have. So for example, if we have a question, something in this nature, we have how many 3-letter words with or without meaning. It means we cannot be able to pronounce them, but it's just a 3-letter word. With or without meaning can be formed out of the letters of the word swing when repetition is not allowed, meaning we cannot repeat any of the number. When I pick the first position, the second position cannot be the same letter again. So imagine I have 1, 2, 3, the first 3 letters. The first one being S. Then it means the X position is over. But if there's a repetition, it means the second word could also be X. So it could be SSI or SSS. That is when we are talking of repetition. But here, repetition is not allowed. How do we do it? First, we have to identify our n, which are the different. So there are 1, 2, 3, 4, 5, 5 different letters of the word swing. Then we need to identify the arrangement, which is R. We have R ways of arranging that. So we are going to have 3 of them, which means we are going to have 5 combination 3 in this calculation to give us the total number of 3-letter words that can be formed from the word swing. From here, we can say that our n, or let's say number of letters of the word swing is going to be n equals what? Let me just say is 5. Therefore, n is what? 5. Then our r equals what? 3, which is just what? 3 letter words. Right? We are picking from that. So what are we looking for? We are looking for how many of them. That simply means that I should be having 5 permutation 3, which from the definition says that 5 factorial on 5 minus 3 all factorial, where n, r are featuring in their respective place. That will give you 5 factorial on 2 factorial. Remember what a factorial expansion is: 5 times 4 times 3 times 2 factorial divided by 2 factorial. I ended on factorial, 2 factorial, because I have 2 factorial to cancel with. So this will cancel. So I should be left with, if this and this cancel, this will give you 12, 12, 5, 60. So it means that there are 60 different ways by which we can form 3-letter words from the word swing. So S, W, I, S, I, N, S, I, G. If you continue combining them, where order does not matter, you are going to be dealing with what? 60 different ways. This is the first type of what? Permutation, which we have done keenly for the previous episode. So let's look at the second type, which is permutation when repetition is what? Allowed. We can also get this concept from the first episode where we did fundamental principles of counting 1, which is the product rule, which shows multiplication in terms of factorial. So if I have 3, let's say, numbers to write, let me just make it 8. Then I want to write all these numbers whereby there will be repetition, picking all of them at a time. It means that when I want to create, let's say, 3-letter words, 3-digit numbers, it could be 6, 7, 8. That is the size I'll get. So to me, I'll be having 3 different numbers for the first position. So I should be having 3. Then in the second position, which this is going to be the 100th position, the 10th position, and the 1. So the 100th position is 3. Then how about the position for the 10? If I pick 6, that does not mean that the second position could be 7 and 8. It could also mean that 6 can appear again. Which means I still have 3 choices to pick from. So that means I'll be having 3 for the 10th position. How about the ones column or position? The fact that I've taken 6 doesn't mean that I am left with 2 options to pick from. No, I still have 3 options to pick because the repetition is allowed. So it means I should have also 3. So if we check this carefully from the fundamental principles of counting, we can see that if I have n different numbers which are going to be arranged in either n or r different ways, it's only telling me to multiply the options I get by the number of ways I am selecting it. In this case, I'm selecting 3. So this simply means that 3 exponent what? 3. So when it comes to permutation when repetition is allowed, we are going to be employing what we call exponential form. Exponential form of what? Let me say, ways by which we can pen those numbers. So if, for example, we have an object to be selected from, then we are to do that in R ways, right? We have n objects, but we have what? R ways. That is, this is the way we are going to have, where repetition when repetition is allowed, this simply means that the number of ways by which this can be done should be n ways at each time, n different times. So that is going to give us n times n times n, that is r times. I'll be multiplying the n by itself, the number of options I have. I should be multiplying those options because each of them will be featured in each position, each at a time. You mean at this point, first position will be taken by what? The number of elements that are available. Since repetition is allowed, that number I selected first could have the chance to feature again in the second position. And that could also have the chance to be in the third position, which means each of them have the time to be repeating at all the places the number of n times, number of ways I am to arrange that. So that will simply imply that n exponent what? R, which will give us what we are looking for. Now, how can we deduce this in a particular question? So let's take a question and see how we can do that. Alright, so if we have this, how many three-letter words with or without meaning can be formed out of the letters of the word smoke when repetition is what? Allowed. So it means that repetition of letters is allowed. We are looking for three-letter words, so it could be SSS in all the three places, MMM in all the three places, or MOM. There should be a repetition. It's allowed. Then we need to know number of letters of the word smoke. Is going to be what? 1, 2, 3, 4, 5. So it's going to be 5. That is, our n is going to be what? 5. Then let's go out for R, which is going to be repetition of, three-letter combinations. We have 3. That is, we have 3 as in 3-letter word. Let's say lettered words. You can correct the English as we go forward. Now, this is what we are having for the question. So what do? We are going to say that permutation when we have our repetition when a repetition is allowed, is going to be given by n exponent r, which is 5 exponent 3. I think 5 times 5, 25 times 5 will give us 125 different ways. So we are going to be having 125 different ways. That will be three-lettered if repetition of those letters is allowed. I guess this is different from the first concept where repetition is not allowed. Meaning, in the first place, if I'm going to choose from here, I should be choosing 5 letters. All the 5 letters are liable to be in the first position. But the moment I pick the X, then it means in the second position, I am only having the option of 1, 2, 3, 4. So I can only choose from 4. Then in the last position, since first 2 are taken, you are left with only 3 letters to be taken from. So that brings the difference between repetition and no repetition being allowed. I guess the concept of the two types are clear. All right, so as stated, we have the third type, which is permutation of multiset. So permutation of n different objects. When p objects among these n objects are similar, then q objects of the second kind are also similar, the r objects of the third kind are also similar, and so on and so forth, then the number of arrangement of these n different objects, taking all of them at a time, is given by the n factorial divided by p factorial times q factorial times the r factorial. The ones that are dividing are showing those set of numbers that are performing repetition. This is different from the second aspect that we did. We did repetition being allowed. But in this case, in these n numbers that we are provided, we cannot distinguish two or three of those items or objects. Then we resort to what? The multi-set object. Or let's just say you are having various fruits to arrange, whereby we have 6 apple, 7 orange, or let's say 2 pear. You are going to arrange all of them. But here, apple is apple. So whether it is 2 or not, they are 2 identical apples. So the first apple comes, the second one, you can't tell which one you are placing first. You get the concept. You can also see that the oranges are also going to be the same kind, the same orange. So orange come, orange come, orange come. You can't tell which of them you are swapping their position. This means that there is a multi-set of those numbers from the given set n. So let's look at an example. In how many ways can the letters of the word maintain be arranged? Be arranged ending there simply means that taking all the letters at a time. If you go ahead and follow the first type, which says that 1, 2, 3, 4, 5, 6, 7, 8, 8 letters, picking all the 8 at a time, you might be making a mistake. Because there is A here, and this A, you cannot distinguish which of the A you are referring to when you arrange. So you can still maintain it here. I can write maintain like this, and write maintain like this, and convince you that this A is the one I'm placing here, and this A goes here. You will not be convinced because it is still A. So this concept comes into play. So what do? We can say that the word maintain has what? 8 letters. So we can have our n to be equal to what? 8. Then which also has, let's go, 2 A's. We have 2 A's and n. We have 2 n's. What again? I. We have what? 2 i's. So if I want to represent that, I can say that that implies p being equals to 2 factorial. This is going to be our q equals to 2 factorial, these two numbers. Then our r also equals to 2 factorial. Now, the ones that are not showing a repetition, meaning they are having 1 factorial. So it could have been m is 1 factorial, t is 1 factorial. And we know 1 factorial being in the denominator will not change the result. So we maintain that. So our arrangement, we can say the required number of what? Ways that we are looking for based on the formula here, which I will not be quoting, is going to be 8 factorial on 2 factorial, 2 factorial, 2 factorial. From the formula, if formula is quoted, this will be the second approach. But since we are having that, what do? We are going to have this to be, okay, let's say we have 8 times 7, 6, 4, 3, 2, 1. I could have bring in a factorial, but let's leave it that way. This 2 factorial is going to be 2 times 1, which is 2, times 2 times 1, which will also be 2, 2 times 1, which will also be 2. So in this case, 2, 2, 2, that will be 8. So 8 will be cancelling this. So we'll be left with 7 times, let's multiply that and see. So when you multiply 7 by 6 by 4 by 3 by 2 by 1, that will give you 5040. So we are going to have 5040 ways of arranging the word, the letters of the word maintain, whereby in this case all the letters are going to be taken at a time, but there is a repetition of some of those letters. I believe we can understand that. So this brings us to the types, the 3 types of permutation. This will not end here. In subsequent examples or episode, we will take questions randomly on each of the types, basically on the second and the third types, since we have a lot of tutorials on the first type, to bring us to appreciate the 2 different approach relating to the second and the third type. When we exhaust all avenue, then we move on to combination. So don't miss out in the series. This is episode number 9. We'll continue to see how many episodes we can get to in this lecture. Don't forget to subscribe to the channel, share with somebody, invite them to subscribe to the channel. Let them click on the notification bell so that anytime a video of this kind is uploaded, they will be the first to be notified. Don't forget to leave a comment in the comment section for us to get interactive as a one family. Like the video after you finish watching. Bye-bye.